Okay. Assalamualaikum warahmatullahi wabarakatuh. We are from group 9 that consists of me, Afiliani, Hanif, Salma, and Ardian, Damar, Jodi. Will present the on material section 3.4 that is subsequence and the Bolzano Weirstrass Theorem. Next. The first is the definition of subsequence. Let x is equal to xn be a sequence of real number, and let n1 is less than n2 less than etc. until less than nk be a strictly increasing sequence of natural numbers. Then the sequence x accent is equal to xnk given by xn1, xn2 and etc. so on until x and k is called a subsequence of x. The example: if x is given by the set of 1 over 1, 1 over 2, 1 over 3, and so on, then the selection of even indexed term produces the subsequence is x accent equal to the set of 1 over 2, 1 over 4, 1 over 6, and so on until 1 over 2k, where n is equal to n1 is equal to 2, n2 is equal to 4, and so on until nk is equal to 2k. Other subsequence of x is equal to 1 over n are the following: the set of 1 over 1, 1 over 3, 1 over 5, and so on until 1, 1 over 2k minus 1, and the set of 1 over 2 prime, 1 over 4 prime, 1 over 6 prime, etc. until 1 over 2k prime. The following sequence are not subsequence of x is equal to 1 over n is the set of 1 over 2, 1 over 1, 1 over 4, 1 over 3, 1 over 6, 1 over 5, and the set of 1 over 1, 0, 1 over 3, 0, 1 over 5. A tail of sequence is a special type of subsequence. In vector, the m-tail corresponds to the sequence of indices is n1 equal to m plus 1, n2 is equal to m plus 2, and etc. until nk is equal to m plus k. But clearly, not every subsequence of given sequence need be a tail of the sequence. Subsequence of convergent sequence also converge to the same limit, as now shown. Next, 3.4.2 theorem. The theorem said that if a sequence x is equal to xn of real number converts to a real number x, then any subsequence x accent is equal to xnk of x also converts to x. The proof: let epsilon is greater than 0 be a given, and let k epsilon be such that if n greater than or equal k epsilon, then the absolute value of xn minus x is less than epsilon. Since n1 less than n2 less than blah 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 until less than nk is increasing sequence of natural numbers, It is easily proved by induction that nk is greater than or equal to k. Hence, if k is greater than or equal to k epsilon, we also have nk greater than to k greater than or equal to k epsilon, so that the absolute value of x and k minus x is less than epsilon. Therefore, the subsequence x and k also converge to x. For the example, the question limit b as powered by n is equal to 0 if 0 less than b less than 1. For the solution, we have already seen in example 3.1.11b that if 0 is less than b less than 1 and if xn is defined by p powered by n, then it follows from Bernoulli inequality that lim xn is equal to 0. Alternatively, we see that since 0 is less than b less than 1, then xn plus 1 is equal to b powered by n plus 1 less than b powered by n is equal to xn, so that the sequence xn is decreasing. It is also clear that 0 is less than or equal to xn less than or equal to 1. So it is follow from the monotone converge theorem 3.3.2 that the sequence is convergent. Let x is defined by limit of xn. Since x to n is subsequence of xn, it follows from theorem 3.4.2 that x is equal to limit of x to n. Moreover, it follows from relation x to n is equal to b powered by 2n is equal to p powered by n powered by 2, and it is equal to x n powered by 2, and theorem 3.2.3 that say that x is equal to limit of x to n is equal to limit x n powered by 2 is equal to x squared. Therefore, we must have either x is equal to 0 or x is equal to 1. Since the sequence xn is decreasing and bounded above by b less than 1, we deduce that x is equal to 0. Next, 3.4.4 theorem. The theorem says that let x is equal to xn be a sequence of real numbers, then the following are equivalent. First is the sequence x is equal to xn does not converge to x element of R. The second, there exists an epsilon 0 greater than 0 such that for any k element natural number, there exists n k element of natural number such that nk greater than or equal to k, and the absolute value of x and k is minus x is greater than or equal to epsilon 0. And the third is there exists an epsilon 0 greater than 0 and a subsequence x accent is equal to x and k of x such that the absolute value of x and k minus x greater than or equal epsilon 0 for k element of natural number. For the proof, from the first to the second, if xn does not converge to x, then for some epsilon 0 greater than 0, it is impossible to find a natural number k such that for all n greater than or equal to k, the term xn satisfies the absolute value of x and k minus x less than epsilon 0. That is, for each k-element natural number, it is not true that for all n greater than k, the inequality of the absolute value x and k minus x less than epsilon 0 holds. In other words, for each k, not the element of natural number, there exists a natural number nk greater than or equal to k such that the absolute value of x and k minus x greater than or equal to epsilon 0. And from the second to the third, let epsilon 0 be as in the second, and let n1 is element of natural number be such that n1 greater than or equal to 1, and the absolute value of x and 1 minus x is greater than or equal to epsilon 0. Now let n2 element of natural number be such that n2 greater than n1 and x n2 the absolute value of x n2 minus x is greater than or equal to epsilon 0. And let n3 element of natural number be such that n3 greater than n2 and the absolute value of x n3 minus x is greater than or equal to epsilon 0. Continue this way to obtain the subsequence x accent is equal to x and k of x such that x and k is such that the absolute value of x and k minus x is greater than or equal to epsilon 0 for all k-element natural numbers. And the next proof is from the third to the first. Suppose x is equal to xn has a subsequence x accent is equal to x and k satisfying the condition in the third. Then x cannot converge to x, for if it did, then by theorem 3.4.2, the subsequence of x accent would also converge to x. But this is impossible since none of the terms of x accent belong to the epsilon 0 neighborhood of x. Since all subsequence of a convergent sequence must converge to the same limit, we have part 1 in the following result. Part 2 follows from the fact that a convergent sequence is bounded. Next is 3.4.5 Divergent Criteria. If a sequence x is equal to xn of real numbers, has either of the following properties, then x is divergent. The first is x has two converged subsequence x accent is equal to x and k, and x double accent is equal to x r k whose limits are not equal. And the second is x is unbounded. For the example, the sequence x is defined by -1 followed by n is divergent. For the answer, the subsequence x accent is defined by -1 followed by 2n is equal to the set of 1, 1, and so on. converts to 1, and the subsequence of x double accent is defined by minus 1 powered by 2, and minus 1 is equal to the set of minus 1, comma minus 1, and so on, converts to minus 1. Therefore, we can conclude from theorem 3.5, the theorem 3.4.5 first, that x is divergent. Next is the existence of monotone subsequence. 3.4.7 Monotone Subsequence Theorem. The theorem says that if x is equal to xn is a sequence of real numbers, then there is a subsequence of x that is monotone. For the purpose of this proof, we will say that the m term xm is a peak if xm is greater than or equal to xn for all n such that n is greater than or equal to m. That is, xm is never exceeded by any terms that follows it in the sequence. Note that in a decreasing, every term is a peak, while in an increasing sequence, no term is a peak. Next proof, we will consider two cases depending on whether x is infinitely many or peaks. For case 1, x has infinitely many peaks. In this case, we list the peaks by increasing subscripts is equal to xm1, xm2, and so on until xmk. Since each term is a peak, we have xm1 is greater than or equal to xm2 is greater than or equal to so on until it's greater than or equal to xmk. Therefore, the subsequence xmk of peaks is a decreasing subsequence of x. For the case 2, x has finite numbers, possibly zero of peaks. Let this peak be listed by increasing subscript is equal to xm1, xm2, so on until xmr, and let s1 is defined by mr plus 1 be the first index beyond the last peaks. Since xs1 is not a peak, there exists s2 greater than s1 such that xs1 less than xs2. Since xs2 is not a peak, there exists s3 greater than s2 such that xs2 less than xs3. Continuing in this way, we obtain an increasing subsequence xsk of x. It is not difficult to see that a given sequence may have one subsequence that is increasing and another subsequence that is decreasing. The next is Bolzano Weirstrass Theorem, and it will be explained by Ardian Damar.
Okay, for the next is 3.4.8, the Bolzano Weirstrass Theorem. We will now use the monotone subsequence theorem to prove the Bolzano Weirstrass Theorem, which states that a bounded sequence of real numbers has a convergent subsequence. We can see the proof is It follows from the monotone subsequence theorem that if x is equal to x with index n is a bounded sequence, then it has a subsequence x accent is equal to x with index nk that is monotone. Since this subsequence is also bounded, it follows from the monotone convergence theorem, which states that a monotone sequence of real numbers is convergent if and only if it is bounded. Thus, the subsequence is convergent. It is readily seen that a bounded sequence can have various subsequences that converge to different limits or even diverge. For example, the sequence -1 powered by n has subsequence that converge to -1, other subsequence that converge to +1, and it has subsequence that diverge. Let x be a sequence of real numbers and let x accent be a sequence of x, then x accent is a sequence in its own right, and so it has subsequence. We note that if x double accent is a subsequence of x accent, then it is also a subsequence of x. For the next is 3.4.9 theorem. Let x is equal to x with index n be a bounded sequence of real numbers, and let x element real numbers have the property that every convergent subsequence of x converges to x. Then the sequence x converges to x. We can see the proof for theorem 3.4.9. Suppose m is greater than 0 is a bound for the sequence x, so that the absolute value of x with index n is less than or equal to m for all n element natural numbers. If x does not converge to x, then theorem 3.4.4 implies that x is epsilon 0 greater than 0 and a subsequence x accent is equal to x and k of x, such that the first equality is x and k, the absolute of x and k minus x greater than or equal to epsilon 0 for all k element of natural numbers. Since x accent is a subsequence of x, the number m is also bound for x accent. Hence, the Bolzano Weirstrass Theorem implies that x accent has a convergent subsequence x double accent. Since x double accent is also a subsequence of x, it converts to x by hypothesis. Thus, it is term ultimately belong to the epsilon 0 neighborhood of x, contradicting to the first equality. For the next is limit superior and limit inferior. The theorem 3.4 definition 3.4.10, let x is equal to xn be a bounded of real numbers, and we have a the limit superior of x with index n is the infimum of the set v of v element r, such that v less than x with index n. For at most of finite number of n element natural number, it is denoted by lim supremum xn or lim sub x or lim with upper bar of xn. Next, for the b, the limit inferior of xn is the supremum of the set w of w element real numbers, such that xm less than w. For at most of finite number of m element natural number, it is denoted by lim inferior of xn or lim supremum or lim infirmum x. There is a typo, and or lim with underbar xn. For the next is 3.4.11 theorem. We have that if xn is a bounded sequence of real numbers, then the following statement for a real number with x powered by star are equivalent. We have A x powered by star is equal to lim supremum xn, and B if epsilon greater than 0, there are at most a finite number of n element natural number such that x powered by star plus epsilon less than x with index n, but an infinite number of n element natural number such that x powered by star minus epsilon less than x with index n, and C if um is equal to supremum of xn with n greater than or equal to m, then x powered by star is equal to inferior of with m element natural numbers is equal to limit and we have D if S is the set of subsequential limits of xn, then x powered by star is superior S. And the next is 3.4.12 theorem. We have that a bounded sequence of xn is convergent if and only if limit superior xn is equal to limit inferior xn. Proof, we have that in inferior of x with index k with k greater than or equal to n less than superior x k with k greater than or equal to n. From the order limit theorem, we get that limit superior xn greater than limit xn greater than limit inferior xn. And we have that if limit superior xn is equal to limit inferior xn, then by squeeze theorem we get limit xn is equal to limit superior xn is equal to limit inferior xn. Conversely, if limit xn exists, then say limit is x. From convergence definition, given any epsilon greater than 0, there exists n element natural numbers such that the absolute value of xn minus x is less than epsilon. The next proof is for all n element natural numbers, but for any k greater than or equal to n, so the absolute value of superior xk with k greater than or equal to n minus x less than epsilon, which implies limit superior xn is equal to x. Similarly, that the absolute value of inferior xk with k greater than or equal to n and minus x less than epsilon, which implies the limit inferior xn of xn is equal to x. Therefore, we have the proof is limit superior xn is equal to limit inferior xn and limit is equal to limit xn. Okay, that's all from our group presentation. Sorry for our lack and mistake in this presentation. Me, Ardian, Damar, and my friend Afiliani, Salma, Hanif. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.